Well, I hope you feel like you were able to give some of these a try, and maybe you have an extraneous solution in there that we need to get rid of, but don't worry about it. And if you got stuck and you're just here to see how I do it, that's great too. Let's start right away with the first one, and for a lot of you it looks funny because the 5 comes before the square root, so some of you prefer to rewrite it like this. Either way is fine. If we're going to solve this, we don't have a graph. We could sketch a graph. That would be a great way to solve it. And if you did that, good for you. But I prefer to solve this one by undoing personally. First, subtracting the 5. And then to undo a square root, we use a square because those are inverse operations. And so x minus 2 would be 9, making x equal to 11. Now that felt pretty straightforward, no issues. We could see that 11 is the solution here. If we wanted to test it, we could double check. 11 minus 2, that would be 5 plus the square root of 9, which would be 5 plus 3, which is in fact 8, so that works out just fine. So x equals 11, should feel pretty confident with that one. If we take a look at the next one, okay, we're again solving by undoing. So we do the addition and subtraction first. This one has got some multiplication and division for us to tackle. Everything is feeling pretty straightforward so far. To undo that square root, we use a square. And we see 49 equal to x plus 4. Subtracting 4, we've got 45 equal to x. Hopefully you don't have any questions there. Should make pretty good sense. And if we're being thorough, we can just test it out by trying what happens when we input 45. Then we see that we have 3 times the square root of 49. I'm running out of space, so I'm just going to borrow some over here. So 12 is equal to 3 times 7, which is 21. When you subtract 9 from 21, you get 12. So it works out. 12 equals 12. So no problems with extraneous solutions so far. So if you got x equals 45 for this one, you're in good shape. This next one is where you may have gotten the best possible wrong answer. Oh, there's the bell. So if we were to address this kind of without thinking things much past undoing, we would see that we would subtract 10 from both sides if we're solving by undoing. And this is pretty similar. So here we've got 3 minus 10, which would be negative 7. Negative 7. And put a little circle around that. That's an interesting development. But we can continue on. We can take x plus 4, we can square it. We can take negative 7, and we can square that as well. So we would have x plus 4 equal to 49. By subtracting 4, we would see that x might equal 45. And this would be the best possible wrong answer. So if you got 45, you did great. Unfortunately, what we have here is an extraneous solution. And I'm going to show you a couple of different things. First of all, if we were to plug it in, right, 45 plus 4, take the square root and add 10, does that actually equal 3? Well, 45 plus 4 is 49. And the square root of 49 is 7. Does 7 plus 10 equal 3? Does not. That's an extraneous solution. So you might be asking yourself here, well, how was I supposed to know that this was an extraneous solution? And that comes all the way back up here. All right, when we were looking at the square root of x plus 4 and it equals equals negative 7. All right, that's the extra solution. Think back to when we were working with squares. And we were thinking about the square root of 25, and we thought, oh, the square root of 25 is 5, but it's also negative 5. That negative 5 is the extra solution. When we're solving square roots, we got to watch out for those extra solutions because they don't exist on the graph. Let me show you this another way before we move on. All right, so if you thought perhaps that x was equal to 45, let me show you why it can't actually work out that way. Take a look at this and think of a quick sketch. Okay, so this has been moved left 4 and up 10. So left 4 and up 10, and it's a square root graph, and so it looks something like that. So here we are at -4, 10. But if we're looking to see where this thing equals positive 3, the line for y equals positive 3 would be down here. And you can see from this quick sketch that our solution line, y equals 3, never crosses our square root graph. They just don't ever intersect. Therefore, there's no solution. So this has no solution, even though you may have gotten 45. And this will be tricky for us for a long time. We'll talk some more about this tomorrow. If you did try the last one, this last one was a little bit of fun. It looks kind of complicated because you have 2 radicals. But you'll notice that those radicals are alike. They can be considered like terms. So one of the things we can do here is we can subtract 7 square root of x plus 1 from 12 of them. Right? If I have 12 and I take away 7, then I have 5 left over. 5 square root of x plus 1 equals 10. Again, if that went too fast for you, 12 minus 7 is 5. Just thinking about combining like terms because those radicals are alike. Then if we divide by 5, square root of x plus 1 will equal 2. Notice that's a positive, so we're not going to be dealing with extraneous solutions. Square both sides, and x plus 1 equals 4, making x equal to, that's right, 3. So again, the key with extraneous solutions happens when you're just about ready to make the square step. So right here, when we had equal to -7 and we were about to square it, that was our clue that we were going to have an extraneous solution. Compared to here, when we were about to square it, and we had a positive to square, we knew we weren't going to have extraneous solutions. Again, we'll do more with this in class tomorrow. Go ahead and try the last task, which is a graphing task.